3. Geometric progression. Geometric progression deal with product. So the first term is a, the second one is a times r, the next one is a times r squared. So the n term is a times r n to the n minus 1. For example, if I give you this geometric progression, you have to divide to find the ratio. Now the 6 over 2, and I'm trying to find the fifth term, and the general equation for the fifth term is a times r to the n minus 1, so the fifth term is 162. Find the eighth term of the geometric progression, 6, 4, and so on. Again, what you have to do is divide these over these to give you the ratio. First term is 6, n is equal to 8. Last term is 256 over 729. Seventh term of this, well, you have to take the ratio again. And seventh, 8 r to the n minus 1, 243 over 2048. If you're given the n term, the n, the ratio, you can find the first term using, I'm going to clear values here and give you this equation. A is equal to n r to the 1 minus n. If you know the first term, the n term, you can find the ratio. N over 8 raised to the 1 over n minus 1. For example, the sixth term of the geometric progression, that will be this equation. Whose ratio is 1/2 and its first term is 1/16 is equal to 2. The first and sixth term of geometric progression are 3 and minus 729. So we're going to use this equation right here. We know the sixth term, and then we know the first term. So we take the ratio of them, raised to the 1 over 6 minus 1, and the ratio turns out to be minus 3. As we did with the arithmetic progression, it turns out that the product of two values equidistant from the extremes is equal to the product of the extremes. In the case of the arithmetic progression, it was the sum. And then we can use that to calculate the sum of all the terms. This is the sum of all the terms. If I multiply that by r, I get this result. And then if I subtract this minus this, you get this result. And so that the sum of a geometric progression is given by the last term an multiplied by the ratio r, subtracted the first term and divided by r minus 1. For example, determine the sum of the first 6 terms, that will be n equals 6. For geometric progression, the first term is 4, and the ratio will be 2 over 4. And that last term is r to the n minus 1. And the sum is equal to a 6 times r minus a divided by r minus 1, so the sum is equal to 63.8. Determine the sum of the first 8 terms of the geometric progression. So first term is 9, ratio will be minus 3 over 9. Is for the 8th term, so the a sub 8 is equal to this quantity, and then we have this equation to calculate the sum. Interpolating elements in a geometric progression, we're going to clear all the terms. We find the ratio this way, and as we did for the case of the summation of the arithmetic progression, we're going to take n equal to m over 2, where m is the number of terms, the number of elements that we're going to interpolate. And then we're going to use the make list, where instead of adding, we're going to multiply the ratio to the k minus 1. For example, interpolating n equal 4 elements when the first element is 3 and the last element is 96. N is simply the number of elements in total, which is m plus 2, and the ratio is equal to this. With that ratio given, then we can calculate our make list, put terms 96, 48, 24 down to 3. Cleaning up these values again, summation of the infinite geometric progression of decreasing ratio. So suppose that the ratio is decreasing, is like less than 1. And this is an infinitely long sum. We have this expression for the sum in general, and this is the last term. If we replace this into here, the sum simplifies to this. A times 1 minus r to the n divided over 1 minus r. Now, if r is less than 1, as r increases, r is less than 1, r squared will be less than r, which is less than 1. And so, as n goes to infinity, in other words, when the number of elements in the progression grows very large, this value is going to go to 0. And so, at infinity, this value simply disappears, and the sum for an infinitely long geometric formula, the geometric progression, sorry, is equal to the first term divided by 1 minus r. So it's as simple as, in this case, they gave us r 2/4, a or 1/2, and a equals 4. Since it's a decreasing ratio, then the sum of all the infinite terms is equal to 8. How about this one, the infinite progression? The ratio is minus 310, is absolute value is negative, is less than 1, sorry. So the sum is equal to 50/13. For example, if we have a periodic decimal like this, 0.333, that never ends, we know that we can write this as 3/10, 300, 3,000. And so each element in the sum here represents an element of a geometric progression. The first term is 3/10, and the ratio will be 3/100/3/10, which is 1/10. The first term is 3/10, and the sum will be a/1 minus r, which is equal to 1/3. In other words, the infinite decimal 0.3333 is equal to 1/3. So something that we suspected. Here's another example where we have 0.3, 3/10, and then the 15 repeats over 1,000, or the next one will be over, what is that, 1,000,000, and so on. And so the ratio will be, this is the second term in the progression over the first term, which is this one. The first term is this one, and we're going to keep this as an addition, as an extra addition. But the sum of the term from here down is calculated this way, 1/16, and then we add to that the 3/10. So the number that we're actually trying to represent with 0.315515 is 52/165. We can check that by doing float of the last value. And indeed, Maxima, of course, will give us only 15 elements, but obviously is a repeating decimal. And so this is a quick presentation of geometric and arithmetic progressions, something that we're going to be useful in the next video on logarithms. So we'll finish talking about progressions with this video.